fun.
When you look up the night sky, you will see dozens, if not more, stars, even in the city. These stars are essentially giant balls of churning molten gas that shine so bright that they can be seen across the galaxy. However, despite their size and the giant burning status, they don't last forever. When a star much larger than our own sun begins to die, it explodes with massive force in what's called a supernova. The matter that was just blasted apart from the star very quickly collapses in upon itself, and the gravity therein compresses the matter smaller and smaller and smaller until it forms a hole in space. These are black holes. As defined by the Cambridge group for relativity and gravitation, black holes are defined as a region of space-time from which nothing can escape, not even light. Black holes are so powerful with their gravitational field that they can warp the very fabric of space itself. And even closer, they cause time dilations. Any matter and any light that falls into a black hole is consumed and destroyed. Now, before we go any deeper into black holes, let me begin by explaining one of the very important features of them. On the inbound journey to a black hole, there's a boundary, a spherical region, which marks the point where light heading outward is no longer fast enough to actually escape the black hole. Light travels at 670,616,629 miles per hour. That's over 2 million times faster than a powerful tornado on Earth, and more than 10,000 times faster than the Earth rotates around the sun. Matter falling into a black hole is pulled in by the gravitational force, and it spins around the black hole, much like the Earth does with the sun, getting closer and closer to the actual hole of the black hole, being sucked in much like water is down the drain. Now, let's say by some miracle of science, we go to a black hole, and we send out a person to go in and explore this black hole. This person would be pulled in by the black hole, and the immense gravity therein would begin to stretch their body in a process that's known as spaghettification, which causes the actual molecules to be stretched by the increase in gravity. The closer you get to a black hole, the more intensely the gravity is, and the more uncomfortable it would get, until it reached a point where your body was ripped apart and pureed down to its most basic elements. While it's impossible to observe black holes directly, due to the fact that the event horizon allows nothing out of it, we can, however, observe black holes by the decimation that they leave around them. Another important part of the black hole is the very belly of the beast. The very belly. This is a point far deeper, beyond the event horizon, that is a point of infinitely dense mass that is utterly incalculable. Now, we only have theories about what this point is, what it looks like, and what exactly it does, but it is called the singularity, and it is essentially the driving force behind the gravitational pull of the black hole. Now, I prepared a model to better illustrate just how a black hole affects space. If you can imagine space as a flat sheet, then this right here would be the black hole. Remember, all that mass that was once a star condensed down to one single point, getting heavier and heavier, occupying a smaller and smaller space, which sinks down into space, creating a hole, just like this. The event horizon would be somewhere in here, where the gravitational pull has already pulled down the actual fabric of space, and somewhere below that is the singularity. Now, perhaps more interesting than a black hole's effects on matter and space is its effects on time. Due to the intense gravitational pull, time is actually dilated once you get very close into the black hole. Let's say By another miracle of science, we went back to a black hole. And just for the fun of it, we threw a clock in. That clock, as it got closer and closer to the black hole, would again feel those massive gravitational effects, and it would be destroyed. However, while it was still working, the time according to the clock would continue running normally. Now, let's say by some magic, we got that clock back on. We got that clock, we brought it back, and we looked at it. And we compared the time to a clock that we already had that wasn't subject to the same treatment of a black hole. The time that was kept in the black hole would be found to be running slower than the time that we kept. That's because the time is actually dilated closer into the black hole in the event horizon. It would be running slower by seconds, minutes, or maybe even hours. There is still large amounts of what we don't know, and a very large amount of what we know is just calculation and speculation. As one of my very close friends once said to me, black holes are the zombies of stars. They absolutely consume light, and they let absolutely nothing out. Around them, time and space become unhinged, and due to the event horizon, there is no information that we can obtain directly from black holes. However, there is plenty that we can learn still. Scientists will continue to research and observe them, and mathematicians and physicists will continue running numbers over them. These vicious bits of spaces will continue to remain a mystery for quite some time.